Today we're going to be talking about multi-class classification with linear classifiers. So all the stuff we did the last couple classes earlier this week, we only talked about binary classification, meaning there are just two classes. And we first talked about the interpretation of the weights or the coefficients being a hyperplane that's slicing the space into two half spaces, this class and that class. And then we talked about the probabilities, and then we talked about loss functions on Wednesday. And today we're going to extend things to more than two classes that we're trying to predict. I just want to go back to this notebook from last class. And we had some stuff at the end that there wasn't time for, so I just wanted to go through that now. Okay, we did this. We talked about support vectors. And we talked about, so we talked about if I remove all the things that are not support vectors, then everything stays the same. If I remove support vectors, then things change. And we interpreted the support vectors as in terms of the loss diagram. So if I scroll up to here, we had this flat part of the hinge loss at the right, which were these points that somehow didn't matter for the fit, and those were the ones that were not support vectors. And then we had all the rest, and those were the ones that were support vectors. And there's two ways to become a support vector. You can be in this red area, meaning you're incorrectly classified, or you can be in this blue area between 0 and 1, meaning you're correctly classified, but somehow it's a close call, or you're close to the decision boundary. Okay, so the stuff we didn't have time for is here. So there's this issue of the margin, and as I was rushing at the end of last class, calmly, we talked about how the margin is the distance between the hyperplane and the closest points to the hyperplane, and how SVM somehow maximizes that. So I just want to show you some pictures of what that looks like. So here's logistic regression being run with default hyperparameters on this problem. And you might say, well, I'm not very happy with this because why is it so close to the blue points and why is it so far away from the red points? And that's really dependent on the regularization. So if I axe the regularization, make it really small, then we get something different that maybe you feel happier about. But here's the SVM. And regardless of the amount of regularization I use here, it's cutting exactly between the 2 points, and that's this issue of the margin. So again, the margin is defined by the distance between the hyperplane and the closest points. And so it's, in other words, the minimum distance from the hyperplane to the points. And if SVM maximizes the margin, then it maximizes the minimum of the distances. And I had mentioned, either in class or on Piazza at some point, this flavor of maximizing the minimum of something, that it would show up at some point. So this is, I guess, as I mentioned at the end of last class, maybe the traditional approach to talking about support vector machines. And the reason why we opt for the other approach, which is basically talking about the hinge loss as a convex approximation to the 0-1 loss, is that the margin, it's interesting, but it's much easier to talk about when the data set is actually linearly separable, which is usually not the case, and has to be extended properly when the data set is not separable. And then the math has quite a lot of steps, some of which are not that intuitive to get from this to that. But amazingly, saying that SVM has to maximize the margin plus a little bit added onto that for when your data set is not linearly separable is actually mathematically identical to hinge loss with L2 regularization, which is a pretty nice result. Okay, this is sort of an aside, but I also just wanted to say that KNN with k equals 1, we wouldn't really use the word margin, at least I haven't seen it done when talking about this, but it actually kind of had this flavor as well if we think back to what it's doing, because the boundary is going to be equally distant between the points of the two classes when k equals 1, because the color at each point in the picture is just the color of the closest point. Any questions about this? Tom?
You go back up just one picture. So we're trying to minimize the distance to the nearest point on each side.
We're trying to maximize the distance to the nearest point.
Okay. Thanks. Okay.
That's it?
Yeah, no, sorry.
Okay. Yeah. So if I move the boundary a little bit, then the nearest point would become closer. So by having it halfway in between, this margin is maximized. Okay. Just a few other comments. So we talked a lot about probabilities with logistic regression and outputting probabilities. And there are ways to sort of coerce an SVM into giving you probabilities, but it's not really natural in the way it is for logistic regression. So it would be more common to see probabilities coming out of logistic regression. In terms of regularization, I propose that we revisit the issue of regularization when we talk about kernels on Monday, because actually it's kind of it's interesting. So this max margin thing I claim should work under a range of regularization situations. Well, that's killing it with too much regularization, but okay. So I think that now we're moving a little bit. In any case, I think the best thing to do is leave the interpretation of regularization until Monday. Although I guess it's a bit subtle. Okay, finally, just to preview what's going to happen on Monday, we're going to get these things to learn us nonlinear looking boundaries. So if this picture looks interesting, then come to class on Monday. Okay, on to today's stuff. So as a motivation for today's lecture, we'll talk about part of speech tagging. And this is a task that we'd like to perform on natural language data. And for example, we might want to find where is the verb in a sentence. So the 340 students jumped at the chance to hear about part of speech features. We know that we know how to identify the verb, but for a machine learning algorithm, this is a challenging problem to understand, especially because there's so much ambiguity in language, especially English, which is, I think, a pretty difficult language with a lot of exceptions, redundancies, ambiguities, and all that. So this is a labeling problem or a classification problem, and we want to classify each word. But we don't just have two classes. We have a whole bunch of possible part of speech labels we might be interested in. And of course, this is just one motivation, but it's not hard to think of all kinds of multi-class situations in image recognition. Is this a cat or a dog or a mouse? But really, you might have 100 or 1,000 different classes of wanting to identify what's in an image, and so on and so forth. So one thing I want to talk about first is what type of features we should use for each word. So for each word, we're going to have some features and use those to predict the part of speech. And as we talked about a long time ago at the beginning of the course, we can convert categorical features. So the labels are multiple labels, but the features might also be categorical. And if we have a categorical feature, like in this example, the city, Vancouver, Burnaby, Surrey, we can make a new column for each feature and use this 1 of k encoding to encode that. So one type of feature we can use for words is these so-called lexical features, where we have some information about a word, and just based on the word itself, it tends to be this part of speech or that part of speech. We can also look at the previous word. So for example, if we're trying to classify hit as being a verb or a noun, we might want to know the previous word. For example, he hit versus a hit now changes the interpretation of the word hit. We can look at the word even before that, the word after that, and so on. So another thing we can do is look at the letters inside of a word. So we can have all these different types of features for words helping us classify the part of speech of the word. And for this example here, does it end in ing? So that's an example where that feature might be a pretty strong indicator of the word being a verb. And then we can have other types of binary features about the particular word that might help us tag part of speech. Here comes Mohammed. He can probably tell everyone much more about this than I can, but that's okay. Don't worry about it. Okay, so that's an example of why we might want to do multi-class classification, and just a bit of a digression for fun about types of features you might use for this type of thing. But we're not really focusing on the types of features today. We're focusing on the output, the category, and the fact that we want to use linear classifiers for multi-class. So this is what we've been doing so far. Some features, some labels, -1, 1. And this is what we want to do today. Some features and some labels in some set of things. In this case, you might have a whole lot of classes, apparently more than 27. But you might even just have 3 classes, and even for 3 classes, we haven't yet talked about how to apply linear classifiers. So it's important to note that the methods we used in the first part of the course, decision trees, naive Bayes, KNN, they didn't care if there were 2 classes or 3 or 10. And in fact, you implemented these methods in your assignments, and you applied them to multi-class classification problems. For KNN, well, you're just looking at the labels of the nearby things. So those could be whatever. It doesn't matter, right? You're just taking the most popular one and predicting that. For decision trees, when we get to a leaf, we're just taking the most popular class and predicting that. And for naive Bayes, we just need to store these conditional probabilities, and if there are more possible classes, we need to store more things, but everything generalizes really naturally. So it's kind of unusual in the context of this course that we have to do all this extra work to get to multi-class, and yet for linear classifiers we haven't gotten there yet because they're just slicing the space in half. Okay, so there's two main approaches I want to talk about today. And we'll start with the so-called one verse all or one verse rest approach. And this is not specific necessarily to linear classifiers, but this is just sort of a meta thing you can do to turn binary classifiers into multi-class. So, yeah. You can take as input whatever binary classifier and apply this strategy. And here's how it works. When we're training, we keep a separate binary classifier for every class. So if we have 5 classes and we're doing logistic regression, we're just going to keep 5 separate logistic regression objects. And the first one's going to learn class 1 versus not class 1. The second one's going to learn class 2 versus not class 2. Third one, and so on and so forth. So each classifier is going to be solving a binary classification problem. But then we have this overarching framework to combine all of them. And the way we're going to make predictions is we're going to get each classifier to produce a score for each class. For example, for logistic regression, that could be the probability. So the first classifier might say I'm 95% sure it's class 1. The second classifier might say I'm 30% sure it's class 2, 40% sure it's class 3. Then I'm going to go with class 1 because it has the highest score. Any questions about what one versus all classification is? We'll talk more about the details, but questions on what it is that I'm describing? Connor?
So for training, does that mean you have to do like the whole process of training k times?
Yes. For training, it means you have to do the whole process of training k times, each time on a data set of the size n, the original size. So we expect this to be, I guess, k times slower than what we were doing before, which, well, how bad that is depends on k. Allie?
The score is how likely it is.
Well, I was using probability as an example of a possible score, but as I was mentioning, this is sort of a meta method. So I could use this for whatever classifier, and maybe that classifier doesn't have the ability to output probabilities. But if I'm thinking of this in terms of like an API or what does the thing need to do so that I can do this to it? Well, as long as you give me something that can output some sort of score, then I can do this even without knowing necessarily what that score is. Mohammed?
What if actually one example testing that same score for one versus all for 2 types of?
Can you say it again louder?
What if we actually for the test example it gets 70% for a class and then a 70% for one versus all for another class? How should we choose something like that?
Yeah, okay. So are you asking about tie breaking? I mean, we'll need some sort of tie breaking rule here. Maybe logistic regression, even a binary logistic regression, maybe outputted 0 or 0.5 probability, and we need some sort of tie-breaking rule there. So it's the same thing. We'll need some sort of tie-breaking rule here, which can just be arbitrary. And we've had this problem before with K and N and decision trees and all these things. Okay, so just to walk through it, if we're trying to classify an image as containing a cat, a dog, or a person, then the first classifier will predict +1 if it's a cat, and -1 for dog images or person images. Classifier 2 will look for dog and be -1 in the other cases, and so on and so forth. So you're leaving X the same, but you're changing Y in each case. The training labels. You're changing them from the multi-class labels to the binary labels. Okay. So we're going to use the notation capital W to be a matrix of weights that stores all the weights for the individual classifiers. And we're sort of intentionally being consistent. A matrix W tends to show up pretty often in this course, and it may mean different things at different times, but we're just trying to keep it always K by D just to keep things easier for you. So for example, with K means, we also had a matrix W. Each row is containing one of our means. That's not the same thing as here, but most of the time W will be of size K by D, meaning a collection of K vectors that live in our original space, just to keep things a little more straight. Right. So, and writing it in matrix notation like this gives us these convenient things, like we can take W, multiply it by a vector x, then the matrix multiplication essentially gives us each row times x, and we get all these scores, and then we can take the maximum. And we can even multiply a W matrix by an X matrix and just write things in neat, convenient ways. Okay, so one concern you might have about this, and I don't know, maybe this is what Mohammed was asking earlier, but one thing that could worry you is I said take the largest score, but if you actually look at the scores, those scores are supposed to have interpretations. They're supposed to be linear classifiers. The score being positive means something. The score being negative means something, right? Positive +1, negative -1. So sure, we can just take the biggest score without thinking about it too much, but what if we actually get something positive multiple times? So we have, yes, we can still take the maximum, and that'll work, but it's maybe a little worrying that it might think it is a cat and it is a dog, and then I'm just going to pick one of them. So this taking the maximum of W transpose X, that is specific to linear classifiers. If you're doing this with a classifier that's not a linear classifier, you could take the maximum score for some other definition of score. If it's logistic regression, then taking the biggest W transpose X or taking the biggest probability, those are equivalent. Because to get the probability, we just take the output W transpose X and pass it through a sigmoid, and that's a monotonic function. So whichever had the biggest raw score, that's going to have the biggest probability, and vice versa. Okay. Here is what these boundaries look like. So before we had boundaries that were just a hyperplane cutting things in two. And now we have, in a way, a whole bunch of hyperplanes. And we're looking at each point which one is biggest, and then we're coloring in the region. So as the slide says, the blue region is the case where the W blue transpose X is bigger than that same thing for all the other colors. Philip? In the top left, are there any points there? I think we just can't see them. Yeah. So there would be no point having a fifth classifier if there were no points of that class. Yeah. So I think this is just, I can see them very vaguely. Yeah, this is just a poor visualization. Yeah. Okay. So these are the types of surfaces that we're expecting to learn. These are convex regions like we had with k-means. Not that we're doing clustering. I mean, we're not even doing unsupervised learning here. But we have actually seen these types of pictures before. Now we're doing it with supervised learning. So it's good to see these things to just keep in mind, okay, if I'm going to do this, what can I actually learn, right? And you're going to be learning pictures that look like this, except in higher dimensions. Okay, so I had said before that you might get +1 for dog and +1 for cat or something like that. So I just wanted to point out there are machine learning problems where you want to do that, right? Like you might be classifying an image and you just want to know what's in the image. Is there a person in the image? Is there a cat? Is there a dog? Is this? Is that? And there could be more than one thing in an image, right? So the point of this slide is just to say that is an actual type of problem that you might want to solve called multi-label classification, but it's just not the problem we're talking about today, which is multi-class classification. The difference being that you can have multiple ones in the same row of the Y matrix. Oops. Okay. So in this case, if we fit K binary classifiers and a bunch of them come up as +1, then that's good. I mean, we would like to know that. Whereas with multi-class, using one versus all, we're discarding that information and just taking the one with the biggest score. Okay. Talked about this. Talked about this. Okay, so in terms of notation, we'll sometimes write W sub Y sub I. That means for the ith training example, the true class is yi, and then that W. So the weight vector corresponding to the true class for that training example. That's what W sub yi means. And the motivation, so I said I would mention two general strategies today for multi-class classification for linear classifiers. This is the end of strategy one, which is one versus all or one versus rest, where you just train separate classifiers on different data sets, where each data set has the Y values binarized in a different way. And the motivation for the second part is this, well, partly this issue that you might have multiple things coming up positive, but also this issue that we didn't train the classifier in a way that was fully consistent with how we used the classifier, because we just trained each of those classifiers completely separately. So in a sense, we solved K independent D-dimensional optimization problems. The next thing we're about to do is we're going to solve a single K times D-dimensional optimization problem. We're going to say, let's learn that whole W matrix all at once in maybe a more clever way than this, so that they kind of, each one knows about the whole problem instead of just knowing about its own binary classification problem. And on the assignment, you'll try out both of these things. And these are kind of standard approaches. So for example, if you look at scikit-learn, the logistic regression class, it has a hyperparameter for which multi-class strategy you want to use. And then there's one versus rest, or multinomial is the one we're about to talk about. Okay, so can we come up with a loss that does all this thing at once? Yes. We're going to talk about it for logistic regression in particular today, and you can also do this for SVM, and there's stuff in the bonus slides about that. Okay, as usual, I prefer to start by talking about how we make predictions and then talk about how we're going to train the thing. So if we're entangling everything together instead of having separate problems, we should also change how we make predictions. And here's how I like to think about this. So we talked last time about the sigmoid function, and with logistic regression, you get this score, this model output, W transpose X, and then we pass it through the sigmoid because we want to take a number and make it between 0 and 1, and then it's a probability. We can interpret it as a probability when it's between 0 and 1. So now we have K numbers coming out of this thing, and we want to interpret them as K probabilities. So we need some mapping that takes K numbers and does something to all of them so that they are all between 0 and 1. There are many ways of interpreting the function I'm showing you on the slide, but my personal way that I like to interpret it is okay, I have a bunch of numbers. I want them to be probabilities. My first problem is that they're negative. So I'm just going to take exp of all of them, and then they're not going to be negative. Great, I solved that problem. And then I also wanted them to add up to 1. So I'm going to just divide by the sum of them, and then they're all going to add up to 1. So that's what's happening on the slide, if you look at it, right? Your probability for yi being some particular class C, you're taking the W transpose X for that C. You're taking exp of it, so now it's non-negative. And then you're dividing by that same value, but for all the classes, so now you know that all these probabilities are going to add up to 1. Okay, and this thing is called the softmax function. And the reason why it's called softmax, I don't remember. Have we talked about this already? No. Okay. The reason why it's called softmax is it's sort of a softer version of the max function, or I guess the argmax function, in the sense that if you took x of some giant number, like 1,000,000 times W transpose X, if you scaled this thing up a lot, then what's going to happen is because the exponential function grows so quickly, of all those terms in the denominator, the one that's biggest is going to completely dominate all the rest of them. And the reason why I feel like we've talked about it before is because it's the exact same argument when we talked about the log sum x smoothing of the max. So it's the same way of thinking as that. And in fact, they're very related. So if I had some big number there, then I would just get a probability of 1 for the biggest score, because that term would dominate the denominator, and I would just have that thing divided by itself equals 1, and I would have 0 for all the other probabilities. So it's kind of a softer version of the argmax, something like that. Yeah. Any questions about this? So in fact, we won't get into this in this course, but if you ever encounter someone talking about the temperature of the softmax, it's exactly this thing that I was talking about here. And there's a lot of, I guess, physics history in machine learning, and so this word temperature often shows up through the connections to how these things fit into physics. And essentially, if the temperature is very, very low, then your probabilities are going to be very close to 0 and 1. And it's just what I said. You take those numbers and you divide by t. But that's a bit of an aside. OK, I don't want anyone to be afraid of this equation. So if you are, I mean, with this, it looks kind of weird, but it's actually quite intuitive and definitely very important. So if this thing is bothering you, it would be a good time to say something. Ed?
The only thing that kind of bothers me is why W has D dimensions. So it's D, the big W is D by K, but why does
W have D dimensions? Because the linear classifier, all these linear models we're talking about, it's always W transpose X. It's one weight per feature, and we're always taking this weighted sum of the features. So just like in linear regression and logistic regression, we also have our weight vector of length D, and now we just have K of them stacked into a matrix. Okay. So we need a loss function for that thing. We need a loss function that we're going to, again, be solving this one big K times D dimensional optimization problem. We need to come up with a loss function that somehow entangles all the W's, and when I minimize the loss, it starts doing a good job. And what does a good job mean? It means that its predictions will be correct. And what does it mean for its predictions to be correct? It means that WYI transpose X should be the biggest one. So what is max of those things? Max of those things is all the scores. It's the biggest score. So this is saying the biggest score, which is on the right-hand side, should be equal to the true score. It's just a slightly less intuitive way of saying why I should be the argmax of all of my k scores. But we need to write it in this way to get a loss out of it. Okay, so the score corresponding to the true thing should be at least as big as any of the scores. That means our prediction, the biggest score is going to be the correct class. We can rewrite this thing by just moving W yi transpose x to the other side. And then back to this log sum x that I was just mentioning before, we can also smooth out this max. We want to get a smooth loss that has all the nice properties that allow us to optimize it easily. So I'll just apply log sum x. And then we replace the max with the log sum x. And then we say, well, we want this thing to be less than or equal to 0. So let's just make it as small as possible. Let's minimize it. And then we get the softmax loss. Okay, so this thing also looks weird. And I can't say that looking at this for the first time, I'm like, oh, of course, Wi transpose x plus whatever, right? But let's break it down. So basically, you're minimizing, okay? So the term on the left is negative, but you're minimizing. So this is saying make the term on the left as big as possible. That makes sense. Make the score corresponding to the true class as big as possible. Okay, but if the problem is if that was the only thing you were doing, you could just make all the scores really big, and you wouldn't actually learn anything. So let's make the score corresponding to the true class as big as possible, while at the same time penalizing the sum of the scores, so that in general you can't just make them all giant and minimize the loss. So it's like, let's make the score corresponding to the true class big, but in general, let's not make the scores too big in general. That's the right-hand term. And then we have something that starts to make a little bit of sense. And there's a whole bunch of ways to derive this or think about this, and there's some more stuff in the bonus slides about this as well. To me, the weirdest step is the very first step. The very first equation on this slide. Gurinder.
Are we then solving for the respective WCs relative to each other rather than individually?
We are okay. What the thing that's going to happen on the next slide? The only thing we have yet to do is sum this thing over all training examples. This is just for a particular I right now. But other than that, we're just summing it all up and then minimizing it using gradient descent or whatever optimization algorithm we choose to use. And as I was saying before, this is just a single optimization problem that involves the whole W matrix. So I guess, does that answer your question?
Yeah, it does. How is that, I guess, better than just classifying training examples individually and then running all our predictions later through that and just taking the max that we get?
By classifying the training examples do you mean how is this better than the one versus all approach? Is that what you're asking? Yeah. Right. So with one versus all, it's a bit, I guess, vague, but with one versus all, the training you're doing or the loss you're using does not exactly represent what you care about at the end. And the best type of loss is one that really reflects the problem that you care about solving. So the dog versus not dog, you can get very good at that. But there's nothing in there saying if it's not a dog, then you should be careful to have your score smaller than the score for the true class. Because at the end of the day, what you're going to pick is the biggest score across all the classes. So it kind of does the right thing. It pushes things in the right direction. But it's not directly minimizing what you care about. So you can come up with situations where it's going to perform worse. It's not like a crazy thing to do, and I don't want to be pitching this one verse all as a crazy thing to do. It's an incredibly popular thing to do, but it's just not quite as nice as saying, this is what I care about, and I'm just going to make some smoothness approximations and stuff that I understand well, and then I'm just going to solve all of it, versus I'm going to do these things separately and hope that when I'm done, the true one is going to be the biggest score, which is not something I really asked for when I made the loss function. So it's a sort of a philosophical argument, but it's actually related to this thing in feature selection, where in feature selection, why not just do linear regression with L2 regularization and then throw away the features with small coefficients? It's related in that, again, you're not directly solving the problem you intended to solve. So, the loss doesn't know that if it sets a W to 0.05, you're in some post-processing step, you're just going to throw away that W and set it to 0. So it's just doing its best on a problem that isn't actually reality later on. And it's a similar thing here. And those type of two-step processes tend to sometimes have pathologies or worse performance than just, here's what I want to do. Here's a function that's small when I'm doing it well. Let's minimize that function. Okay, so as promised, what we have yet to do is sum this thing over all training examples and add regularization. Okay, so our regularization has two sums because our W is a matrix now. Instead of just summing over features like usual, we're also summing over classes because we're regularizing all of our W's in the matrix. Okay, so I guess I talked about this intuition. The left term tries to make it big. The other one tries to make them small. And this thing behaves nicely. It's convex, smooth. One weird thing about it is that when you set k equals 2, it doesn't immediately appear to just reduce down to good old logistic regression because you actually have twice as many parameters. Your W is now 2 by D, but in binary logistic regression, W is just a vector of length D. So the bonus slides talks about the equivalence between this thing with k equals 2 and plain old logistic regression. But that is sort of weird, I guess. So if you think it's weird, that's perfectly reasonable. There are ways of doing multi-class logistic regression where W is a k minus 1 by D matrix. But it turns out this is going to be more natural for us, especially for what's coming later in the course. Fred?
Is there a particular reason why we're using L2 regularization?
Is there a particular reason why we're using L2 regularization? No. I mean, you can use whatever you want. Yeah. This would just be the most kind of boring standard version of this. And, easy to optimize and all that. Okay, another piece of notation that we're going to be using a lot throughout the course is this Frobenius norm. It has a funny name, but it's just the sum of the squares of the elements of a matrix, or the square root of that, I guess. So nothing too crazy going on here. Just generalizing our good old L2 norm, which operates on vectors, to this norm, which operates on matrices. It's just doing the exact same thing, summing everything up. But it's nice because we can use this notation to write our regularization in a more compact way. And we'll be doing this plenty in the next few weeks. Okay. Liam.
Would we always use gradient descent?
Would we always use gradient descent? No. And I've said this before, but I'm happy to say it. I can't say it enough in this course. we teach gradient descent, and we'll soon talk about stochastic gradient descent as the only two optimization algorithms that we cover in this course. But I do not want you to leave the course under the impression that those are the only two optimization algorithms. There's a lot of people, the deep learning community is all about stochastic gradient descent, and it's become a pretty big community there. And there's kind of this vibe that stochastic gradient descent is the only optimization algorithm worth doing, which is just not true. So these things depend on a lot of factors, like the nature of your loss function, the size of your data set, and maybe the accuracy to which you care about solving your problem, or your personal trade-off between speed and accuracy, and all sorts of different things. So since we've only talked about gradient descent in this course, sure, that's how you would do it. But there are definitely other methods that can solve this in many fewer iterations than gradient descent would need. Liam?
Could we not just differentiate it and zero it?
Oh, thank you, Liam. Can we not just differentiate it and set it to 0? So if you recall, in my lecture on gradient descent, I said, and you may ask, can we not just differentiate it and set it to 0? And let me reiterate what I said then, which is differentiating is not the hard part. Setting something to 0 is not the hard part. It's finding the W, the variables that make that equation true, which is the extremely hard part. And the gradient of this thing is some weird function. And if I ask you to find the W matrix that makes that weird function equal to the 0 vector, good luck. You're not going to be able to do it, right? Except through some iterative method, such as gradient descent. So if you would like to think of gradient descent as an optimization method, that's the preferred way of thinking about it. But another way of thinking about it is an iterative method that is trying to get the gradient towards 0. And you start at some place where the gradient is not 0, and you keep moving and moving and moving until the gradient is 0, and then you stop. So the solving of the equation blah equals 0 and optimization, they're very related problems. And they're both happening at the same time when we run gradient descent. Okay, so we talked a little bit about word features at the beginning for part of speech tagging, which was this target application for multi-class classification where you had a whole bunch of different classes trying to say what part of speech each word was. We talked about one verse all, also known as one verse rest, where you can take any binary classifier that is capable of producing a score, not just hard predictions, and turning it into a multi-class classifier, including logistic regression and SVM, where a natural score is W transpose X. We mentioned that multi-class SVMs exist, and by that I mean we did some fancy stuff with logistic regression to get it to be directly a multi-class logistic regression, not the separate problems. You can do the same thing for SVM. And then we talked about the softmax function. Softmax loss has a whole bunch of other names. I don't know if softmax loss is the preferred name, but sure, we talked about the softmax function and the accompanying loss that allows us to solve this one big optimization problem and get multi-class logistic regression. So that's it for this week. That's it for linear classifiers. I'll see you next week. Have a good weekend.